Today we're going to go over into chapter 3 and looking at what we have and continuing on with functions. And we're going to be looking at, along with functions, what will be regarded as inverse functions as well as what will be regarded as one-to-one functions. And for what we have in the case of functions, going back, okay, so we have by definition, okay, for a function, okay, we have a mathematical relation where in the xy coordinate system, and we have for each x value there will be only one corresponding y value. And we've had various types of functions like odd functions, even functions, rational functions, quadratic functions. And now just looking at the subcategories. Okay, we have within the family of functions, okay, we're going to have what is regarded as a one-to-one function. And by definition, a one-to-one function is going to be a function whose inverse is also going to be a function. And just kind of providing a little bit of background. Okay, when we first looked into functions, okay, we had what was referred to as the vertical line test. Okay, and okay, now from a visual standpoint, now all functions will satisfy the vertical line test. Okay, but what is going to separate a one-to-one function apart from the other functions is that a one-to-one function is going to satisfy the vertical line test and also what is going to be the horizontal line test. And basically, what it's saying is that while a function is stating that for each x value there's only one y value, well, the one-to-one function you have that plus you have a little inversion of the language, or putting things in reverse where we have for each y value there is only one corresponding x value. Now, just for what we have in the case of examples of one-to-one functions. And just like whenever we first looked into functions, okay, we had looking at ordered pairs, and we'll do the same thing here. And we'll say that we have first case. Okay, we'll say we have f of x is equal to, we'll say we have the set of ordered pairs. Okay, where we'll say we have 1, 3. 2, 5. 3, 7. And we'll throw in 4, 9. Okay, so we at least have a function case. So we have 1 is paired up only with 3, the x value 2. We have only paired up with 5. 3 is uniquely paired up with 7. 4 uniquely paired up with 9. Okay, and now just again, just going back to domain. The domain is the set of x values. Okay, so we have 1, 2, 3, and 4. And for the range, that's going to be the set of y values. Okay, so you have 3, 5, 7, and 9. Now for this given function, okay, when we mentioned, okay, going back to the definition of a one-to-one function, we have a function whose inverse is also a function. And for what we have for this given function, notation we're going to be using, okay, this would be like, well, let's say f to the -1 of x, okay, but now we're not looking at like taking the reciprocal of these x and y values. What we are looking at in the case of inverse, in the context of what we have regarding functions, is where we're going to have the x and the y coordinates will interchange. So the inverse function is going to have the coordinates with the x and the y value switched. Okay, where f of x had 1, 3, the inverse is going to have 3, 1. Before we had 2, 5, the inverse will have 5, 2. And in contrast to 3, 7, okay, we have 7, 3. And where we had 4, 9, the inverse has 9, 4. And for the inverse, okay, now the domain. Okay, this time we have, for those x values, we have 3, 5, 7, 9. And for what we have in the case of the range, okay, it'll be the set of the inverse functions, y values, to have 1, 2, 3, and 4. And just for what we have in this particular case. All right, so we have with the term inverse. Okay, and notice you have swapping domains and ranges. So we want to have a one-to-one function and its inverse. we'll have interchanging x and y values. And just another case of a one-to-one function. Now say we have g of x. And we'll say we have g of x. Okay, so we'll say that we have -1, -4. And say we have 0, 6. As well as 2 and 13. Okay. All right. So we have for this function. Okay. So for the domain, you have the set of x values, and again, it doesn't matter what order you place the x terms. They could be in increasing order, decreasing order, jumbled order, but as long as you have the x values and only the x values. So the domain we have consisting of -1, 0, and 2. And for the range, okay, we have 3 distinct y values. And those values we have -4, 6, and 13. And for the inverse of g of x, again, just swapping out the x values for the y, and vice versa. So we have -4, -1, and followed by 6, 0, and 13, 2. And for what we have in the case of the domain, okay, so you have -4, 6, and 13. And for the range, again, we have -1, 0, and 2. Again, so you have essentially interchanging domains and ranges. All right, now for what we have, going back to the graphing feature of a one-to-one function, again, a one-to-one function is going to satisfy both vertical and horizontal line tests. And then we have just like on the basis of looking at items from a graphing perspective. Okay, let's say and we'll say we have in the first case here. Okay, so just putting in the XY coordinate system. At least putting in the X and Y axes. And we'll say we have a line and we'll say that for this function, okay, we'll say we have that y is equal to f of x is equal to x plus 2. Okay, and okay, so just Again, so we're going to have at least a function, again, by applying the vertical line test. Okay, so you have from end to end, you have intersection by at most 1 point, okay, between the vertical line and anything that we have shifting from left to right, okay, for what we have for the given function. Y is equal to x plus 2. So you have the intersection no more than 1 point. Okay, now for what we have in the case of a horizontal line test. Okay. So if I move vertically, again, you're going to have intersection by at most 1 point. Okay, so in this particular regard, okay, y equals f of x equals x plus 2. Yes, that is going to be 1-to-1. And let's say that if we have and we'll say that we have an absolute value function. Okay, so the absolute value of x, or y is equal to the absolute value of x, okay, that is going to be a function. It does satisfy the vertical line test. However, in the case of the horizontal line test, okay, as we go up, okay, especially once you get past the origin and you start to go up the least bit, you're going to have, at the same y value, you're going to have 2 points of intersection. And for what we have in effect, okay, this particular function, because we have 2 points of intersection between the horizontal line and the function at the same y value, okay, the answer to this question is going to be no. So y equals x plus 2, it is 1-to-1, and y is equal to the absolute value of x. It fails the horizontal line test, so that is going to be no. And let's say that if we have let's say we have a curve Okay, so you have y is equal to f of x is equal to x to the third. Again, for this part, okay, it is going to satisfy the vertical line test. So it meets the minimum standard in terms of defining a function. Okay, so it does satisfy the vertical line test. Now, in terms of the horizontal line test, to see whether this function is a 1-to-1 function or not. Okay, so we have with the horizontal line, so if I move up, okay, have intersection by at most 1 point so far between the horizontal line and what we have for the function y is equal to x cubed, so I have intersection at most 1 point. And so in this particular case, all right, so y equals x cubed. That's going to be a 1-to-1 function. And say if we have y is equal to f of x is equal to x to the fourth plus 1. Okay, so first of all, okay, it is a function, and whether it is going to be 1 to 1, and guess what? Okay, you have at the same y value, you have 2 points of intersection between the horizontal line and the graph of the function. And so once again, the horizontal line test is failed, just like what we had for the absolute value of x function. Okay, and so while all 4 items will be functions, only the absolute value of x and y is equal to x to the fourth plus 1, because they failed the horizontal line test, these are functions that are not 1 to 1. Okay, and now also for 1 to 1 functions, okay, in terms of how they relate with their inverses. Okay, now a 1 to 1 function and its inverse will compose together as x. Okay, and what I mean by this, okay, say you have a given 1 to 1 function f of x. If f of x is 1 to 1, then the composition between f and its inverse, okay, so you have f composed with the inverse of f of x, and so we're looking at f of the inverse of f of x. And that's going to be equal to x, and it'll also work in the reverse order. We had the inverse of f composed with f of x is equal to the inverse of f of x. And that is going to be equal to x. Okay, and now just kind of a lead in here. Okay, so you have composing together as x. And so kind of lead up to another principle here. That's going to be where we have the graphs of f of x and its inverse. Okay, since they compose together as x, okay, the graphs will have symmetry. They will have symmetry with respect to the line y is equal to x. Okay, so one-to-one function and its inverse will have symmetry with respect to the line y is equal to x. So so the graphs will reflect each other about y is equal to x. All right, now let's say that just looking at some of the cases here, going beyond the looking at ordered pairs and just taking the sampling of whether the graph satisfies the vertical or horizontal line test. And let's say that if we kind of look at determining just what inverses we might have for given functions. And let's say that especially one-to-one functions. Okay, so we'll say for the next part, now let's say if we have, say if we're looking at determining the inverse of the following. And just kind of picking up what we had here. Okay, so you had like our first one-to-one function as we looked at expressions outside just the mere sets of ordered pairs. Okay, we had y is equal to f of x is equal to x plus 2. And we'll see what the inverse of this is going to be. Okay, and we're going to have what will be regarded as explicit and implicit notation. Okay, explicit will be where we had like y in terms of f of x. You're looking at x and f of x, and for the inverse, the explicit we have for that part will be x and the inverse of f of x, whereas the implicit will be just the x and y interaction. Okay, so we got just to kick things off. Okay, so we got f of x is equal to x plus 2. Now the f of x will be in reference to y. Okay, so f of x equals x plus 2, same as y is equal to x plus 2. Now for the inverse, I should say for the inverse, okay, to get to the inverse. I'm going to do it here. So, and function is inverse will have interchanging x and y values. So looking at the interchange, okay, what we have where y is located, we're going to put in x. Where x was, we're going to put in y. So we now got x is equal to y plus 2. And what I'm going to do here is that I'm going to express this equation in terms of y. So I got x is equal to y plus 2. And if I isolate the variable y, I'm going to take 2 away from both sides. So I have the x minus 2 is equal to y. And if I just swap the sides here. X minus 2 is equal to y, or y is equal to x minus 2. Okay, y equals x minus 2. Okay, that is going to be the implicit notation of what we have for the inverse. Okay, so that y, okay, first y we had in reference to f of x, but now after the interchange, this y is going to be not for f of x, but the inverse of f of x. So just with the formal notation case, you have the inverse of f of x is equal to x minus 2. All right, and now just looking at what we have here, at least from a visual standpoint. Okay, so we have in the case of graphing. Okay, so if we look into, let's see. So if we look into Desmos, okay, and that which we started out with. Okay, so you have y is equal to x plus 2. We have y is equal to x minus 2. Okay, and just to mention, okay, so if you look at what we have here, so we have with y is equal to x plus 2 and y is equal to x minus 2. Okay, notice you have with y is equal to x plus 2, we have negative 2, 0, negative 1, 1, 0, 2, 1, 3, 2, 4. Now, if I swap out the x for the y, and notice, okay, between the graphs, okay, we have interchanging x and y values. Okay, so you got 2, 4, 4, 2, 1, 3, 3, 1, along with negative 2, 0, 0, negative 2. And these graphs, again, are going to have symmetry with respect to the line y is equal to x. Okay, so these graphs, these lines are parallel, and they will reflect each other and be equal in distance from y is equal to x. All right, now for what we have in the case of, okay, another function, and we were just fresh off of the one-to-one function where we had that y is equal to x cubed. Now let's say if we're looking for the inverse of this one. Okay, so just kind of starting out, what we have here. Okay, so we got, again, for the explicit notation of the function, using functional terms, we have f of x is equal to x cubed. Again, the implicit notation, we have y is equal to x cubed. And once again, setting the stage and developing the statement for the inverse. Okay, so again, we're looking at interchanging x and y. And here we're going to have the x is equal to y to the third. Okay. All right, so I got x equal to y to the third, and I want to express this equation in terms of y equals. Okay, so we can go ahead and kind of switch out. Okay, x equals y cubed, or y cubed is equal to x. And to transform y cubed to y, we can undo the raised exponent by taking the radical on both sides that have the index number that will match the power to which y is raised. In this case, we'll be looking at the cubic root of y to the third is equal to the cubic root of x. Okay, so the cubic root of y to the third. Okay, so this will be y. And we have that y is equal to the cubic root of x. And again, this y is going to make reference to the inverse of f of x. Again, just restating. Okay, so you have the inverse. So the inverse of f of x is equal to the cubic root of x. All right. And so just kind of taking what we have here. Now keep that y is equal to x line. Okay, so we got y is equal to x to the third. And we have that y, okay, and we have is equal to the cubic root okay, so you got the cubic root of x, okay, and notice, okay, there's like a little bit of a twist tie that is completed, but if we have symmetry with respect to the line, y is equal to x. Okay, so just kind of taking some of the sampling here. Okay, so we have like -2, -2. Let's see. Oops, my bad. Here we go. Okay, so you got -8, -2, -1, -1. You got the origin 1, 1, and also we have 8, 2. Okay, you have y is equal to x. And again, we have our points of intersection, okay, where we have at -1, -1, as well as the origin, as well as 1, 1. And again, okay, so you have a one-to-one function with y is equal to x cubed, and the inverse, okay, this is a case where you're going to have intersecting at 3 points at -1, -1, the origin, as well as 1, 1, and the graphs will have symmetry with respect to y is equal to x. All right, now for what we have as another case, and let's say that if we have, say we have a fraction we'll say that we have g of x is equal to 1/3 of x minus 4 . Okay, so setting the stage, okay, so we got the explicit notation for the function. Again, that g of x will be in reference to y. So you have y is equal to 1/3 of x minus 4. Again, setting the stage for determining the inverse. Okay, so I'm going to swap the variables. just the letters and nothing else, okay? Because like 1/3 of x, like I'm just going to move only the x on the other side and just switch out y and put in place of x, but the 1/3 and the -4, those are going to stay in place. So where you see y, just put x in place and vice versa. So we have x is equal to 1/3 of y minus 4. And what I can do here is that I'm looking at raising the coefficient from 1/3 to 1. So I'm going to make this into a y. So I can just multiply the equation by 3. Okay, so 3 multiplying x, so you have 3x. 3 times 1/3 is 1 times y, so you have y minus 12. And looking at isolating y, so I can add 12 to both sides. So we're going to have 3x plus 12 is equal to y. And so that would be y is equal to 3x plus 12. And that is going to be the implicit form of our inverse function, where this y is the inverse of f of x. Is equal to 3x plus 12. And again, just kind of looking at what we have say in terms of graphing. Okay, so let's get out of this. You just have y is equal to 1/3 of x minus 4. And again, the inverse, okay, we have from not t but y is equal to 3x plus 12. And again, just in the case of the interactions, okay, what I'm going to do here, yeah, so if you notice, we have interchanging x and y values. And I tell you what, I think I'm going to just kind of bring this out to the negative zone. Okay, so we have for the x values, yeah, we'll do this. Let's say you have -3. Yeah, we'll do this in multiples of 3. Okay, so you got this set of values. Okay, you have like -3, -5, -6, -6, -9, -7, and so on. And if I swap out the x for the y values, okay, you can notice, okay, have, and again, both of these graphs, okay, we have symmetry with respect to the line. y is equal to x. Okay, and that's going to cut through the middle, okay, where we have at the intersection point -6, -6. All right, and now let's say that if we have a case also in dealing with fractions, and we'll say in this particular regard, and we'll say we have a function, and we'll call this m of x. And we'll say we have that m of x is equal to x minus 7 over 3. Okay, you can split this up like what we had earlier, like 1/3 of x minus 4. In this case, that'd be like 1/3 of x minus 7/3. Okay, so this m of x, okay, we have, again, that is what we have in referring to y. So y is equal to x minus 7 over 3. And once again, once we interchange x and y, again, we're setting the stage for the determination of the inverse function. Okay, so in the interchange, so we have the statement is going to be x is equal to y minus 7 all over 3. And again, to get rid of the fraction, so multiply the equation by 3. Upon doing so, so we have 3x is equal to y minus 7, and getting the y term by itself. Okay, so if I add 7 to both ends, okay, so we're going to have that 3x plus 7 is equal to y. And expressing in terms of y equals, so you have the implicit notation for the inverse. Explicit is with the inverse of f layout. So you have for the inverse, you have the inverse of f of x is equal to 3x plus 7. Okay, and now again, just kind of looking at this one. So you have that y is equal to x minus 7 all over 3. And again, we had that y. Let me double check here. Where did I have? Yep, y is equal to 3x plus 7. And again, you're going to have interchanging x and y values. And again, both of these graphs will have symmetry with respect to the line y is equal to x. Let's see. There we go. Okay, so you have like for the, let me get rid of this for the model. So for y is equal to x minus 7 over 3, you have these coordinates. So where x minus 7 over 3 has 10, 1, 3x plus 7 will have 1, 10, as well as 0, 7, negative 1, 4, negative 2, 1, and also negative 3, negative 2. And again, the graphs will have symmetry with respect to the line y is equal to x. All right, and looking at what we have in terms of finding out, okay, what the inverse is going to be, okay, and now so far we've had our functions with all real numbers, okay, for the domain, but we'll be looking at some of the functions that will not have quite that type. But I tell you what, just for right now, let's see what we get for the inverse. So if we're looking at determine the inverse function, and we'll say that we have given that f of x is equal to 2x minus 8. Yes, they have a linear function, and just looking for the inverse of that. Let's see what we have for the inverse of f of x, and we'll discuss in the next few moments. Okay, if we're looking for the inverse of f of x is equal to 2x minus 8, okay, so we have starting out, so f of x equals 2x minus 8, okay, so that is the functional notation equivalent of y is equal to 2x minus 8. And again, crossing over to the determination of the inverse, okay, starting out by interchanging the variables. So you're going to have in the rewrite, okay, so we have the x is equal to 2y minus 8, and now we're looking at solving for y. Okay, so we have, after the interchange, I can isolate the y term. Upon adding 8 to both sides, okay, so you have x plus 8 is equal to 2y. And I can change the position at any time from here on out. I think I'll just do it toward the end. Okay, so if I take both sides and divide by 2, okay, so I have x plus 8 over 2 is equal to y. And so we're going to have for the inverse, okay, so you have x plus 8 over 2 and just declaring, okay, so you have the inverse of f of x. You have this equal to x plus 8 over 2, and if you were to separate, you could also write this as 1/2 of x plus 8 over 2, which is going to be 4. 1/2 of x plus 4. All right, and so just kind of mentioning Okay, so you have y is equal to 2x minus 8. And again, we have with the inverse. Okay, so you have x plus 8 all over 2. And again, we're going to have interchanging x and y values. Okay, so you have swapping x and y values, and again, both graphs will have symmetry with respect to the line y is equal to x. Now, for all the one-to-one functions we have dealt with, okay, we've had the domain and the range to be the set of all real numbers throughout. Now, let's say that if we have this time around something that's not going to have all real numbers throughout, and just kind of using as a bit of a segue. Okay, so if we're looking at the domain and the range are the following. And we'll say we have, first of all, okay, we'll say that we have f of x is equal to, we'll say we have f of x is equal to the square root of x minus 5. Okay, now, because we have a radical, okay, you cannot have x minus 5 to be negative. Okay, but now in looking at, okay, what's going to be in the domain, okay, first of all, x minus 5 cannot be negative. Now it can be 0 or positive. So you can say we have x minus 5, okay, can be greater than or equal to 0. And so if x minus 5 can be greater than or equal to 0, well, we have that x can be greater than or equal to 5. And guess what? So this is going to define what we have in the domain. So here we have the set of all values of x, okay, such that x is greater than or equal to 5. And utilizing interval notation, and using the bracket around the 5 thanks to the equal sign, so you have on out to infinity. Okay, all right, so this will be the domain portion. So you have your values of x greater than or equal to 5. Okay, now for the range, okay, now again, it's been a while since we have seen this property. Okay, so you have f of x equals the square root of x minus 5, so we have that y is equal to the square root of x minus 5. Okay, and what I mean by the property, something we've not seen in a while, is going to be the principal square root rule. Okay, so with y is equal to the square root of x minus 5. So in other words, the even root of an expression cannot reduce to a negative constant. And for what we have in the case of y, okay, so y is equal to the square root of x minus 5, okay, so if it's not going to be negative, the square root of x minus 5 has to be either 0 or positive. So in this particular case, okay, the minimum y value is going to be equal to 0, okay, and so the minimum y value is going to be 0. Y cannot be negative, okay, and so this is going to state that for the range okay, this is going to be where you had the set of all values of y such that y is greater than or equal to 0, or using interval notation for the range, they're going from and including 0 on out to infinity. Okay, all right. So for the domain, y is equal to the square root of x minus 5. The domain, you have x is greater than or equal to 5. Okay, and for the range, you have y is greater than or equal to 0. Okay, and again, you have both of these coming from the restrictions imposed regarding the nature of the radical. Okay, now let's say that if you have, along with determining the domain and the range, okay, first of all, let me go with another function here. And we'll say that we have g of x is equal to the square root of x plus 1 minus 4. Okay, so for g of x, okay, so g of x, we have the square root of x plus 1 minus 4. Again, on the side of the domain, okay, the burden is going to rest upon the square root term. Okay, so x plus 1 cannot be negative. Now, x plus 1 itself can be 0 or positive. And in this particular case, we're going to have that x is greater than or equal to negative 1. Okay, and so we're going to have for the domain, okay, so we have the set of all values of x such that x is greater than or equal to negative 1. And again, just in the interval notation, so we are looking at going from and including negative 1 on out to infinity. All right. Now, again, for the given function, now looking for the range, okay, so you have g of x, you have the square root of x plus 1 minus 4, and again, so g of x you have at y is equal to the square root of x plus 1 minus 4. And thanks to the principal square root rule, again, the even root of an expression cannot reduce to a negative constant. Okay, so an even root expression cannot reduce to a negative constant. So just kind of taking from this page and applying here. This time we're going to have the minimum y value. Now in terms of the smallest value that the square root of x plus 1 can be, that is going to be 0. And since the statement has square root of x plus 1 minus 4, the very minimum y value is not 0, but 0 minus 4. From which we're going to have that y is equal to negative 4. Okay, and that is going to be the minimum y value allowed. So we have, in the case of the range, we have the set of all values of y such that y is greater than or equal to negative 4 again, just using interval notation, so you have going from and including negative 4 all the way out to infinity. All right, and now just want to mention, okay, so let's say going back to the first function. Okay, if I'm looking for the inverse, okay, now in terms of laying the foundation, okay, so we got the inverse of f of x is equal to the square root of x minus 5, and just some things to mention. Okay, just sort of laying the groundwork. Since this function does not have all real numbers for the range or the domain, okay, so for f of x equal to the square root of x minus 5, again, for the domain, you're looking at where x is greater than or equal to 5, and for the range, you have the set of all values of y such that y is greater than or equal to 0. And when I swap out, what I have in the range will be what I have in x for the inverse, and what I have in x for this function I'm going to have in y for the inverse. Okay, and now looking for the inverse. Again, so starting out, so you have f of x is equal to the square root of x minus 5. Okay, so we have, going back to the implicit notation, so you have that y is equal to the square root of x minus 5. And now I can interchange. And looking at what we have upon interchanging x and y. So I have that x is equal to the square root of y minus 5. And I want to express this equation in terms of y equals. So to get rid of the radical, I can square both sides. And upon doing so, we have x squared is equal to y minus 5. And now getting y by itself. So I can add 5 to both ends. So I'm now going to have x squared plus 5 is equal to y, and just swapping out. Okay, so we had that y is equal to x squared plus 5. Okay, and applying the inverse notation. So we have the inverse of f of x is equal to x squared plus 5. Okay, now so for the inverse, we have the inverse of f of x is equal to x squared plus 5. And stating the domain and the range. Again, just kind of doing some of the crisscrossing. Okay. There we go. Okay. So again, x and y values will be interchanged. Okay, so for the inverse function, the domain is going to be, again, taking in x, what was taken in y for the original function. So we had the set of all values of x such that x is greater than or equal to 0. Now for the range, we're going to take in y for the inverse, what was taken in x for the domain. So the range will be the set of all values of y such that y is greater than or equal to 5. Okay, now, so just looking at what we have from a graphing standpoint. Okay, so if you notice, you have a y is equal to the square root of x minus 5. Okay, the very minimum y value that exists is going to be 5. Okay, and the range, again, so I'm just kind of mentioning, so for the square root of x minus 5, so anything that is less than 5, we have undefined expressions. Okay, so you have like anything less than 5 for x, you have like 3 is undefined, 4 is undefined, so the minimum x value allowed is going to be 5, and the range minimum y value is going to be 0. Okay, so that part's okay. Okay, so we got, just clearing out the table. Okay, so the domain and the range are already in play. Now, for what we have in the case of y is equal to x squared plus 5, and if you notice, you don't have all the values mirroring each other. Okay, and the reason for this goes back to the fact, okay, that the square root function does not have the domain to consist of all real numbers. And to have everything to tie in together, making sure that everything is going to be, when it's going to be the inverse of the other from start to finish. Again, the inverse function, it's not going to be all of x squared plus 5, but the values of x squared plus 5, where x is going to be a whole number, that is, where x is going to be 0 or more. So making this adjustment, okay, so for y is equal to x squared plus 5, we have whereupon the x is greater than or equal to 0. And guess what? That part is cleaned up, and we have both portions reflecting each other about the line, okay, y is equal to x. So like with your numbers, okay, say x is greater than or equal to 0. So like 0, 1, 2, 3, 4. And for the radical case, we have, we've got 5, 0, 6, 1, 9, 2, 14, 3, and also 21, 4. Okay, so you have all the coordinates, you have interchanging throughout. Okay, and so to make the x squared plus 5 1-to-1 with respect to the square root of x minus 5, you had to constrain what we have in x to be only those values 0 and greater. Okay, so you have complete reflection throughout. Now, and just for the inverse of g of x, and again, just laying the groundwork. Okay, so for g of x, we have the square root of x plus 1 minus 4. Again, the domain, okay, we have the set of all values of x. This is from earlier. So we have the set of all values of x such that x is greater than or equal to -1. And the range, again, we had the set of all values of y such that y is greater than or equal to -4. Now looking for the inverse. Okay, so I'm repeating the explicit notation and putting in implicit terms. So we have y is equal to the square root of x plus 1 minus 4. And if I add 4 to both sides, So we had that y plus 4 is equal to the square root of x plus 1. Okay. And it is at this particular case. All right, so I'm going to be looking at for y plus 4 is equal to the square root of x plus 1. I could interchange to y is equal to the square root of x plus 1 minus 4. I could do it either before or after. Sorry. I was kind of on the pathway to interchanging later. I'll go ahead and get started. Okay, we'll go ahead and interchange. Okay, so what was y becomes x and vice versa. And so we had the y term as the square root of y plus 1. And we can isolate the radical expression containing y. Okay, so we can go ahead and add 4 to both ends. Again, you can immediately interchange, or you can kind of do it at a later stage. Okay, so now we got x plus 4 is equal to the square root of y plus 1. And now looking at squaring both sides. Okay, so if I square out x plus 4, okay, so this will be x squared plus 8x plus 16 is equal to y plus 1. And if I subtract so we have x squared plus 8x plus 15 is equal to y. And so we have, at least in the implicit notation, we have at least the variable expression part of the inverse. We have y is equal to x squared plus 8x plus 15. And going ahead and putting in inverse notation with the mentioning of the domain and the range that will correspond. Okay, so you got the inverse with x squared plus 8x plus 15. And again, for the domain. Okay, now for g of x, I had a set of all values of y whereupon y is greater than or equal to negative 4. But now for the inverse, this will be what I have in x. And as for the range of the inverse, I'll have for this one in y what was in x for g of x. In this case, the range of the inverse will be the set of all values of y whereupon y is greater than or equal to negative 1. and this will be the complete package. Okay, what we have for the inverse. Okay, and so just looking at what we have in the lineup. Okay, so y is equal to the square root of x plus 1 followed by the subtraction of 4. And again, the very minimum value that is already laid out. We have the bottommost point at -1, -4. So the domain and range graphing are already baked in for the original function. Now for the inverse, okay, so again I have y is equal to x squared plus 8x plus 15. Notice I have the entire parabola. And that is not going to be one-to-one with respect to the radical function because, again, the domain of the inverse, while I got the algebraic expression, I'm not going to need all the x values involved. And it's just going to be contained to those values of x such that x is greater than or equal to -4. And you have that containment. You got y is equal to x, and so both graphs are going to mirror each other about the line y is equal to x. Okay, so just kind of, you just have -1, -4. (0, -3), and like 3, -2, 8, -1, 15, 0. And again, a one-to-one function is inverse. Once again, we'll have interchanging x and y values. In this case, we do have consistency throughout. All right, now just a few things here regarding one-to-one functions and relations. Okay, and so far with what we have looked at, okay, we've had dealing with radicals, fractions, quadratic expressions, as well as linear expressions that are one-to-one, and where we had to adjust the domain and the range, okay, to make everything one-to-one, okay, between the function and its inverse. Now there is another kind of situation that requires some level of adjustment in terms of making one-to-one, and this will be in the case of what we have in working with exponents. Okay, and just a kind of a brief introduction, I'll just look at one particular base in this one. And for what we have concerning exponential functions and their inverses. And for what we have here for an exponential function, that we can make one-to-one. See, we have f of x is equal to the exponential base a raised to the x power. And to ensure that this function is going to be one-to-one, okay, just some details here we have regarding a. We say that a is going to be positive with the exception of 1. and also where y, or in this case f of x, is going to be greater than 0. Okay, so to be 1 to 1, okay, so your y value is going to be positive, and the base a must be positive except for 1. And looking at what we have in, say, determining just what the inverse of this is going to be. Okay, so you got f of x is equal to a to the x. Again, f of x, even in the exponential realm, okay, is going to be in reference to y. So here we have that y is equal to a to the x. And just like before with the other operations, we're going to interchange the x and the y values. So we're going to have in this statement, okay, we have the x is equal to a to the y. Okay, now, and we're still looking at expressing this in terms of y equals. But if you notice, okay, we're going to have to undo the presence of a, and here I cannot use like radicals or division or subtraction, addition, or even multiplication. Okay, there's a special operative that we'll be looking into, and this will be for undoing the presence of exponential base. We'll be using what will be referred to as logarithms. Okay, and in this particular case, okay, to get rid of the exponential base a, we're going to use what will be referred to as base a logarithms on both sides. So in this case, you have like log, and you had the subscripted letter a. So this will be in reference to the base a logarithm. In this case, base a logarithm of x is equal to the base a logarithm of a to the y. The left-hand side, okay, we have the base a logarithm of x is equal to, and what's going to happen here is that if you have bases, both exponential and logarithmic, these are going to cancel each other out, and the right-hand side is going to be all of whatever power the exponential base a was raised to. Okay, so the right-hand side is going to be y only. And just switching out, so you had that y is equal to the base a logarithm of x and so we're going to have for the inverse in this case, so we have the inverse of f of x is going to be equal to the base a logarithm of x and just like what we had at the start, now a as an exponential base is positive with the exception of 1, well, as what they regard as a logarithmic base. You have the same thing to be applied where you have a to be positive with the exception of 1. And where the exponential function had y is greater than 0, we have this time around that x is going to be positive. Okay. And so this leads up to a common question. Like, just what is a logarithm? Okay, well, in this particular case, all right, so in terms of what is a logarithm, well, a logarithm is going to be the inverse of an exponential function. again, like swapping x and y coordinates. And just kind of give you a case here in terms of how it could be an inversion. And some of you might have had chemistry courses or earth science courses or physical science, kind of dealing with base 10 arithmetic. And let's say just kind of give you a foundation here. Okay, say you have like an exponential function like f of x is equal to 10 to the x. And I want to find out why the inverse of this is going to be. Okay, so we got that f of x is equal to 10 to the x. Or y is equal to 10 to the x. And once again, if we look at interchanging x and y, okay, so we have x is equal to 10 to the y, and I want to express this in terms of y equals. And guess what? When I had the base to be, exponential base to be a, I took base a logarithms. Well, guess what? With the base at 10, I'm going to be taking base 10 logarithms. Okay, so left hand side we had the base 10 logarithm of x, and on the right it had the base 10 logarithm of 10 raised to the y, and the logarithmic and the exponential basis will undo each other. So again, this will go to y on the right, and then just flipping the order, we had that y is equal to the base 10 logarithm of x and so we're going to have for the inverse, we have the inverse of f of x is equal to the base 10 logarithm of x. Okay, and to show you how the numbers interact, and I'll just kind of do a bit of a quick chart here. Okay, so you got your x value, and you say you have for the exponential function, you have y is equal to 10 to the x. You got your x and y coordinates. Okay, so again, just looking at what we have now. Okay, say you have like x is 0. Oh, sorry, let me back that up. So you have not x at 0, but x at 1. Okay. So we have, in the case of y is equal to 10 to the x. So 10 to the first is going to be 10. So you got 110. Say if x is 2. So you got 10 squared is equal to 100. That 2 100. And for what we have in the case of 3, you have 10 to the third. Okay, so that'll be 1,000. And just throwing some more here. So you got 4, so you got 10 to the fourth. is equal to 10,000. So the x and y values, they have 4 and 10,000. Okay, now in terms of what we have for the logarithmic scale in base 10, now just mention now in your calculator, okay, for the base 10 logarithm of x, many models, it'll be just, you'll see log. You have just log, like log of x. That's just looking at the base 10 logarithm of x. Okay, and let's say we have, in this case, we'll say that we have x at 10. And guess what? For y, you have like the log of 10 is equal to 1. Let's say if x is 100. And we have the base 10 logarithm of 100. That is equal to 2. And for x at 1000, we have the base 10 logarithm of 1000. Okay, that is equal to 3. And the base 10 logarithm of 10,000. Okay, so that is going to be at 4. It's got like 10, 1, 102, 1003, as well as 10,004, and just kind of going back. Okay, so kind of playing with the numbers. So like, say whenever I have 0, now 10 to the 0 is equal to 1. So for that ordered pair, x and y, so that would be 0, 1. And say like if x is at 1, you have like the base 10 logarithm of 1, that's going to go to 0. So that ordered pair is going to be 1, 0. And let's say that if we got like x at -2, or 10 to the -2, that's going to be like the reciprocal of 10 squared, or 1 over 100. Okay, so that's going to be 0.01. And that ordered pair, you would have like -2 and 0.01. And if I had, like on the logarithmic scale, if I had x at 0.01 with a base 10 logarithm of 0.01, that's going to come out to -2. And the xy values, can we have it 0.01 and -2. Okay, so this is like where you had the base at 10, exponential and logarithmic. You're going to have, again, so logarithm is going to be the inverse of an exponential function. Inverse in the sense that you're going to have interchanging x and y values, like 110 to 100, and 1 will lead to 10, 1, 100, and 2 for the others.